this one. So we can reduce the number of switching transmission gate and make the circuit simpler, but it also leads to some vulnerability. Typically, the way flip-flops and resistors are designed, when this is in transparent mode, this one should be in hold mode. When this one is reading a new value, this one should be in hold mode, should maintain its value stable. So inside a flip-flop or resistor, the latches should not be in the same state at the same time. The first one, the controlling one, if it is in copying a new value, this one should be hold mode, maintaining its end value. When this one copies a new value, this should not be taking a new value, it should maintain its own value. So for this to be in transparent mode, this must be in hold mode and vice versa. So if we follow this, because there is nothing disconnecting this loop, when this one is in hold mode, this one is copying a new value, but if this switch is on, the value can actually travel in the reverse direction, can flip this value. So there can be an intentional short circuit or reverse flow in this type of design. So we have to make sure that this one and this one, the delay is carefully designed so that by the time it reaches, it transfers the signal, it cannot contaminate it. So we have to carefully size those transistors that it becomes a ratio design. So, and it will have all the limitation or the challenges of a ratio design if we use this overpowering the feedback loop technique to minimize the number of switching devices. So these are the different approach for making simpler device, simpler resistor or flip-flop. Now let us look at the transistor-based implementation. So this one, we are showing the switches are transmission gate-based. And as we have seen earlier, we can implement each of these latches using only single transistor and MOS transistor. So if we implement a positive edge-triggered latch followed by a negative edge-triggered latch where switches are all single transistors, we get this circuit. It has one limitation. Every time we are passing one, it will be experiencing one threshold voltage drop because NMOS is not very good pull-up device. However, so there is one limitation, we have to live with it if we use transistor-based switch. However, we can improve this design in terms of speed if we do some modification in connection. First, let us look at the operation of this one-bit resistor or flip-flop. When clock is high, this clock is off, so this one will be in hold mode. Because this is on, the loop will maintain its own value. When clock is on, D will get copied here, and then it will be copied here. When clock is off, this will be disconnected, this will be on, it will go into hold mode, this will be on, it will get a new value here, right? But finally, what you are trying to do, you are trying to copy a new value from input D to the final output Q. This flip-flop or resistor, what is its function? It's a memory. It stores the information you apply at node D into the final output node Q. So now, from the application of the input from D, how long the path is? One transistor, two inverter, two transistor, four inverter, right? From D to Q, for you to copy the signal from D to Q, the signal must travel through 4 inverters and 2 transistor, right? So from the time you apply the input at D to the time that that signal is copied correctly and available at node Q, the total timing will be equal to delays of 4 inverter plus delays of 2 NMOS transistor, right? So, however, instead of, because we don't care what is happening intermediate, all we care whether D is correctly copied to Q or not, because Q is my output node from where I am going to take the signal. So, a simple tweaking of the connection, instead of sending the signal from here to here, how about sending the signal from here? This is what Q bar, right? D, 1 inverter, this is D bar or Q bar, intermediate value. I am sending it here. Then in that case, after this inverter, I will get Q here. Then Q should not be taken from here. This becomes Q bar. So after how much time I am getting Q? 1 transistor, 1 inverter, 2 transistor, 2 inverter, right? I am still getting the same value Q copied from D after the delay of 1, 2 inverter and 2 transistors. So overall, the speed of copying Q, D into Q, is decreased by 2 inverter delay. So logically, both circuits are correct, but from performance point of view, same overheads, same number of connections, same number of transistors, but this one will be better. So this is just showing some customized approach to improve circuit. So now the question is, this latch flip-flop or resistor, what we have explained so far, their operation is synchronized by this clock signal or controlling signal. This clock signal determines when a new input can be copied. This signal determines whether this loop is closed or not, whether it will be whole mode or transparent mode. That means every step of the operation, from input D, application of input D to the availability of the output Q, every step is controlled by a synchronizing signal, in this case clock signal. That means all operation will follow certain time steps. To do that, we have to impose some timing control. Now we are going to see what are the timing parameters or time related factors we need to take into consideration to ensure the proper operation. So I'm going to introduce the timing factors of synchronous circuit or sequential circuit here. The first timing parameters in any sequential circuit or in any synchronous circuit. Sequential circuit is synchronous, so I will change those terms interchangeably. For any synchronous or sequential circuit, the first timing parameter is called setup time. Let us put the resistor or flip-flop inside a D box. Inside you have transmission gate circuit or transistor based circuit, whatever circuit you have. First, input is applied to input terminal D, and at some point that input signal will be copied and available at node Q. So between application of the input to the availability of the output, we have to spend certain amount of time. The total time is divided into different time components, and we are going to look at these various components. First one is called setup time. When input is applied at node D, let's say binary 1 is applied. We are talking about digital memory. That binary 1 must be kept stable for a minimum amount of time for this input terminal to recognize that it is a 1, right? if you can open and close the door at like a 1 millionth fraction of a second, you will not be able to probably see whether someone is standing outside the door or not, right? Because human eye has a, I think 1/10 of a second, or there is a sensitivity to time. If the total object, you see an object for less than that amount of time, you cannot recognize it, right? Similarly, it's a physical electrical signal arrived. There has to have some time. It can be a very flickering noise. Whether it is a stable one or not, for the circuit to recognize, before it travels through the circuit, it has to be kept at stable one if you are applying a binary one. That is called setup time. Before the signal starts its journey through the resistor, inside the resistor there is a long complex path, right? So you have to keep the signal stable for certain time before even your clock cycle starts, for the signal to be recognized as a stable one or a stable zero. That is called setup time. So after T setup time, the resistor recognizes that a 1 has been applied to the input. Now it has to be turned on. It has to be turned on, journey begins. Now let us see, for that, now it recognizes that an input high or low has arrived. This one has to be copied through this clock resistance, clock transistor at the input. So, and it will take certain time to go there and latch onto this loop, right? So, at the input, upon activation of the clock signal, you cannot just apply and remove. You have to keep the signal stable for extra amount of time. Upon activation of the clock signal, for this transistor recognize that it is not just a flickering noise, it's a one that needs to be copied here. That means upon activation of the circuit or clock signal, you have to hold the signal stable at 1 or 0, whichever you apply. That is called hold time. Setup time before you applied the clock signal or activated the circuit. Hold time is after you activated the circuit or applied the clock signal. Now the signal entered into the input node, first node. Now it has to travel to 4 inverter 2 transistor or 2 inverter 2 transistor to reach the output node Q. That is the propagation delay of the sequential circuit, right? From application of the clock signal, when clock is activated, circuit is activated, signal will start traveling forward. From that time to the time when it is available at Q, that is the propagation time of the sequential circuit. That is called propagation delay of the resistor sequence circuit, TCQ. It means that from the application of the clock to the availability of the signal at Q, TCQ is the propagation delay. So propagation delay, typically we always follow the worst case path. If you have a complex circuit like this, you may have more than one potential path for the signal to travel from D to Q. So propagation delay is always the worst case or the longest path. If there is a worst case and longest path, there has to be a best case or the shortest path. That is called contamination. There may be inside the circuit some unintentional shortest path or short circuit. Signal may accidentally take that path and arrive at Q while you are trying to maintain hold mode or transparent mode, vice versa. That is called contamination. If such path exists and if signal can travel at a very short time before you finish your two-step operation, that is called contamination delay. It is the minimum delay of any block which a signal can take to travel through the block. Then, if we look at the complete sequential circuit, a sequential circuit is made of a resistor and a combinational block. So setup time, hold time, and resistor, sequential circuit, propagation delay and contamination delay, all these things we are considering for this resistor or flip-flop. But when signal travels from D to Q, now its journey doesn't end. It has to be applied to the combinational logic block. It will take in and it will produce a new output. So it starts from here, its journey ends by completing the loop. For the signal to travel from here to here, there will be a propagation delay. For combinational logic circuit, the worst case and the longest path is its propagation delay. And as we have seen, for different signal combination, there can be a best case scenario which may take the shortest path, which will be its contamination delay. So now, in summary, for any synchronous sequential circuit, there are 4 or 5 timing parameters we have to be aware of. Setup time, it is the time when the input D must be stable or remain valid before the clock signal is applied. Hold time, it is the time when the signal must be kept stable after the activation of the clock signal. And propagation delay of the resistor or flip-flop is the time from the activation of the clock to the time it is available at the output of the resistor Q. Then contamination delay is the minimum or the best possible time a signal can take through the resistor and through the combination of logic block. So there can be a contamination delay for the resistor, contamination delay for the logic block. And then propagation delay of the logic, TP logic, is the worst case, the longest possible delay a signal can take through the combinational logic block. So these are the timing parameters we have to be aware of. Now, among these 5 parameters, hold time is actually embedded inside this propagation delay. Why? Hold time is when, let's say this is the clock signal activation. From the clock signal, hold time is this time when input must be held constant, T hold. Upon activation of the clock signal, you have to keep the input active or stable for a certain amount of time. Once the input is properly copied into the first input node, you can disconnect the input signal. So then it will travel by itself. So, and then the time from the clock activation to the time when the signal is available at Q, that is the propagation delay for the resistor. Clock activation to availability of Q. So this T hold is embedded inside DCQ. Now, for a sequential logic synchronous circuit to work properly, we have to maintain certain relation among these 4 or 5 timing parameters. That is called timing constraints. The conditions or constraint of sequential logic circuit, which is synchronous by nature. There are 2 timing constraints. One is called minimum clock period requirements or constraint. The other one is called T-hold constraint or condition. Now let us look at the minimum clock period constraint. So in a sequential, complete sequential circuit, you have a resistor or memory block and a combinational logic block. Now, and you have to complete the operation of this complete block in 1 clock cycle, right? Because it is controlled by clock signal. Now, so the length of the clock period is T. within that T, clock period length, what are the timing parameters you have to account for? Let's start from here. Before even clock is activated, we have to make sure that we keep the input stable for this amount of time, and during that time, no input should be applied. Right? And then, when input is copied, it will travel from D to Q. Longest possible path it can take, time it can take, TCQ. Then that signal must travel through the combinational block and complete the journey. So I have to have also accommodation for worst case delay to the TP logic. I did not add T-hole here. Why? Because T-hole is embedded inside this. So the minimum length of the clock period required should be equal to or greater than register delay plus logic delay plus setup time. That is called minimum clock period requirement. If your clock period for any sequential circuit is less than summation of these three timing parameters, the circuit will malfunction. What will happen? Whatever if you are trying to send something new will come and it will contaminate the previous value. So, on the other hand, let's say when a new value is copied here, and inside it you have to keep the signal stable for T-hole. Accidentally, if the total contamination delay of the resistor plus the contamination delay of the combinational logic block together, if they are less than T-hole, what will happen? T-hole is the time you have to keep your signal stable here. Otherwise, it cannot copy properly. If the signal takes the shortest path through the resistor and shortest path to the combinational logic block, and if a total contamination time or the time for the shortest path is less than T-hole, a new value will come and it will contaminate or destroy the value you are trying to hold. So, for the circuit to work properly, the T-hole at the input of the resistor must be less than the total contamination delay of the resistor and the logic, otherwise it will destroy the previous value. So these are the two timing constraints. One is called minimum clock period requirements for any sequential circuit to work properly without contamination, and this is called hold time constraint. The total hold must be less than the total contamination delay. If any of these two conditions is violated, the sequential circuit will not work. But these two limitations or constraints or requirements are derived assuming that the clock signals are ideal. What does it mean? Between clock and clock bar, there is no overlap. When clock is going up, clock bar perpendicularly should go down at the same time. But as I explained in the last class, between clock and clock bar, at a minimum, there will be one inverter delay. Because if clock signal is available, you want to get the clock bar, you have to send it through a what? An inverter. So, one of the key requirements for this type of resistor to work is that the clock signal should be 100% non-overlapping. When clock is high, clock bar should go low. So these two timing constraints are derived assuming that the clock signals are ideal. There is no overlap. Later in lecture 8, we will see that we have to add some additional factors into this and this requirements for sequential logic circuit. So now, if you know what should be the minimum length of a clock period should be, even under ideal clock condition, then we should be deriving it from here. If you know the minimum clock period length, that gives you another very valuable information. What is that? Maximum speed you can achieve from this circuit. So from these simple timing factors, you can actually achieve the maximum possible frequency that can be achieved from this type of circuit. So you know the ceiling of the frequency. So if you explore a design beyond that ceiling, your design will not close, right? You will not find a design solution. So that this type of simplistic analysis, these are not accurate at all. There are lots of other factors that need to be calculated to get the actual frequency, but this provides you the minimum clock period length, thereby it gives you maximum possible ideal clock frequency you can achieve. Practically, it will be significantly less than that. So, one of the problems, as I mentioned, in any flip-flop or resistor design is expectation is clock signal will be 100% non-overlapping. Practically, because of the presence of at least an inverter between clock and clock bar, there will be this overlap area during that shaded portion, right? When clock is going up, clock bar will go down probably after some time, one inverter delay. When clock is going down, clock bar will go up after one inverter delay. So during this overlap, what will happen? During this overlap, the way this latch or flip-flop is designed, when this clock signal is, this clock transistor is on, this one should be off. When this one is on, this one should be off. But during that shaded overlap time, there will be a tiny period of time when all clock transistor will be on or all clock transistor will be off. Right? We may run into a situation for 0-0 overlap, right? For 1-1 overlap, all transistor can be on. That means from the beginning to end, the entire path will be transparent. But the way the flip-flop and resistors are designed, if this one is copying, this one should be in hold mode because that transistor should be on. So when you are copying a value from D to this intermediate node X, yes?
Sorry, can you just compensate for that by defining your setup and hold correctly?
Yes, you actually asked the question and answered the question.
Sorry.
Yeah. So by playing with the whole time, how do we play with the whole time? Let's say the signal you copy it from D to A. From A, it will be traveling through one inverter through node X to clock bar to the second one. But if the delay of the first clock and the first inverter total, which is an indicative of the whole time, because it has to be copied from D to that intermediate node, that is your whole time. If that delay is longer than the overlap time itself, by the time it travels from D to intermediate node X, this clock will be over that overlap time, it will be shut down, so it will not be basically competing. So what I am getting here, so the delay, let's call it clock 1, right? So the delay of the clock plus delay of the one inverter, the total delay, sorry, it's not visible. Hey, where is my... So,
Still carry.
you are the lifesaver, right?
Oh, sorry.
So now let me draw this. So I have, it is called T1. I have inverter 1, inverter 2, T2, right? So when you are applying the signal at D, it is coming here, it is going through this, right? You have another transistor here. This is T1, this is your inverter 1, this is your T2. If the delay of T1 plus inverter 1 is greater than delay of T2, right? Then what will happen? So by the time the signal travels through the intermediate node, that overlap is taken care of. So if this remains on, this will become off. So it can let its own value through its own feedback loop, so it will not be transparent here. So carefully selecting the size of this inverter and transistor, we can basically make sure that by the time signal travels from D to intermediate node X, this overlap period is gone. So if this is on, this will remain off. So now to answer your question, how do we calculate hold time? Hold time is when the signal is properly copied at the input of this inverter, which will latch an opposite value at the output of this inverter. So we have to keep that signal stable at D for long enough time for it to transfer from here to here and get copied by the inverter. So that is an indication of the hold time. If that hold time is larger than the delay of the second transistor, which is true, but if we can make, larger than the overlap time, then by the time it reaches the second clock bar, that transistor will be off. So we have to make sure that clock inverter and clock wiring does not impose a delay or overlap more than the combined delay of this transistor and this inverter. Otherwise, there will be a race condition between the value the second latch is trying to hold and the new value that is being injected. So, to avoid this race condition, people thought about many different approach, and one of them is, well, let us not send clock and clock bar to an inverter. Use two independent clock signal, phase shifted by this amount. Two NMOS transistor, one operated by the phase 1 clock, the other one, second one will be operated by phase 2 clock, and those two different clock signal intentionally is delayed by this. So, since there is an intentional delay inserted between two independent clock signal, clock 1 and clock 2, so there will not be any period of overlapping or transparency between first clock and the second clock. So race condition is avoided. But the problem is, there is an idle time for both clock. That means both input switch and the intermediate switch both will be off. If both are off, then this intermediate node and the final node will be floating at certain point. Here we are talking about static sequential circuit where a final node or output node should not be in a floating state. So we are making the circuit pseudo-static. For this short period of gap between two clock phases, the nodes are disconnected. This input node is disconnected, this is off, so that output node is disconnected, intermediate node is disconnected, so we are making a bunch of floating nodes for a short period of time. In any static circuit, it is not designed as a dynamic storage-based circuit. It is dangerous to keep it in a floating state for a long time. So we have to make sure that this gap is not very long. Even it's for a very short gap, the circuit will remain in a floating state a static circuit will remain in a floating state for a short period of time. That's why we are calling it pseudo-static resistor. It's a static resistor, but it will experience a floating state for a short amount of time. So, yes, it solves one problem, but it introduces another problem. So now, up until now, everything we have discussed, latches, flip-flop and resistor, it is based on the cutting the feedback loop and also the overpowering the feedback loop. But when overpowering the feedback loop, we still have a switch here. We removed one switch, but we did not remove this switch. Still, whenever we don't want any input signal to go in, we turn off this switch. Now we are going to introduce a second type of latch or flip-flop that will be purely based on overpowering feedback loop, no switch involved. That is called SR latch. One of the most common memory element that is called SR latch, the fundamental building block of many digital memory circuit. So changing the states of bistable circuit, overpowering the feedback loop, second approach. So a simplest possible SR latch can be made of two NOR gate or two NAND gate. In NOR gate based implementation, those are, each one of them will be two inputs gate. Whether you NOR based implementation or NAND based implementation, in both implementation, there will be two independent input line denoted as S and R, set and reset. S stands for set, R stands for reset. And the other input of this two input logic gate will have a feedback connection to the output signal. The one corresponding to signal S will send the output back to the input to the one corresponding to R and vice versa. And the output Q will be taken from the second NOR. In this case, if we implement with the NAND gate, the output will be taken from the output of the NAND gate corresponding to S. So this is a NOR-based implementation of SR latch. This is a NAND-based implementation of SR latch. Why it is called set reset or SR latch? By applying a value here, you can set the value of the output Q. If you apply 1 here, it will copy 1. If you apply 0 here, it will copy 0. The other node will have the opposite value. If you apply the same here, it will reset it to the opposite value. So only thing you have to remember, in NOR-based implementation, output Q comes from NOR gate corresponding to R. Q bar comes from NOR gate corresponding to S. In NAND gate implementation, it's opposite. So now, if I apply 1 here, 0 here, this will become 1. As applied value will be copied to Q, this will become 0. Similarly, if I apply 1 here, 0 here, it will be 1, it will be 0. If I apply 0 here, 1 here, it will be 0, it will be 1. Set, reset. The question is why? Why NOR gate? This is XNOR gate, right? So NOR gate, because if you look at the very basic definition, if you apply 1 here, right? Irrespective of what you apply in the second, for any it will be 0. It is 0, it is 0, 0, 0 will set it to 1. This 1 will come reinforce here, 1, 1 will set it to 0. This 0 will come, 0, 0 will set it to 1. So we'll keep it 1. So if I apply 1 here, 0 here, unless I change, forever it will maintain 1 here, 0 here. If I flip the condition 0 and 1, they will change. So that's why it's called set reset latch. But now, and this is the most popular latch we used. So now let us look at all possible combination of values at these two input. So it's a 2 input, 2 output circuitry, right? So SR latch fundamentally is a 2 input, 2 output circuit. For 2 input circuit, there can be 4 possible combinations of input. 0, 0, 1, 0, 0, 1, 1, 1. Right? Now for 0, 0, if it is 0, this one will determine what would be its value. If it is 0, this one will determine what its value. So with 0, 0, they will maintain its own value. Right? Q will be Q bar will set the Q. So with 0, 0, output will be opposite of this one. This output will be opposite of this one. So Q and Q bar will maintain its own value as it is. For 0, 0 input combination, we call it that SR latch is in whole mode. It will be holding its own value for 0, 0 input combination. When I apply 1 here and 0 here, it will set the value of Q equal to 1, Q bar equal to 0. When I apply 0 here and 1 here, it will set the value of Q to 0, Q bar to 1, reset. Hold, set, reset. But what happens if I apply 1 and 1? With 1, independently this NOR gate should produce a 0. With 1 here, this NOR gate independently should produce a 0, because if any of the input in a NOR gate is 1, output should be 0. But logically, it is impossible. If Q is 0, Q bar has to be 1. If Q is 1, Q bar has to be 0, right? So, if I apply 1, 1 input combination, both Q and Q bar is 0, then logically it is incorrect. That means for this type of SR latch, 1, 1 input combination is not allowed. So it is called forbidden state. So SR latch can have only 3 possible logical states. 0, 0 in whole mode, 1, 0 set mode, 0, 1 reset mode. 1, 1 is called forbidden state or forbidden mode for the SR latch. But the problem is, if you insert this SR latch inside a complex logic circuitry, which is getting signal from all over the chip, can you guarantee that this 1, 1 signal combination will never appear? No. Because it is random. You don't know what function you are implementing, what information you are storing and processing. So it is impossible to make sure that there will never be a 1, 1 combination at the input of SR latch. So it is one of the biggest limitation of SR latch. So we have to find a way to avoid that. Yes.
I think you're moving in the direction I was going to ask.
Yeah. So we have to find a way to avoid that. So first of all, so avoiding that, we'll talk about it a little bit later, but this type of SR latch, what we are using it for? Using it for storing value at the output as a memory element. So if we have to use it, we want to use it in sequential logic circuit, copying, setting, resetting of data must be synchronized with a clock signal. So we have to modify this circuitry, basic building block, to add the clock control. How can we do that? We can send the signal into the basic SR latch through AND gate, to AND gate. One input of the AND gate is controlled by clock signal. The other 2 inputs are set and reset. Now how the clock signal will impose the control or synchronization? when clock is 1, that one is going to this AND gate and this AND gate, right? For an AND gate, if one signal is 1, 2-input AND gate, the other signal will determine the output, right? For an 2-input AND gate, if one signal is 1, right? Let's say this is signal S. If it is 1, it will be 1. If it is 0, it will be 0, right? For a 2-input AND gate, if you set one value to 1, the value of other signal will determine the output, right? If one of the signal is 0, no matter what you do here, it will be always 0, right? So now, when clock is 1, this AND gate, its output will be determined by R. When clock is 1, this output will be determined by S. So now, when clock is 1, S is 0, S is 1, R is 1, then 1 is applied here, 0 is applied here. So with clock 1, the latch is transparent. You can apply, set and reset without any problem. When clock is 0, irrespective of what you do, this will be getting 0 and 0 because AND gate, 2 output will be 0, so it will be in whole mode. So we are adding a clock control when a new value of S and R can go in, and at the same time we are preserving the ability to put the latch into whole mode by making clock equal to 0. So in the SR latch, 3 allowed state: whole mode, set mode, reset mode. And we can achieve all these 3 modes. Still we can have control by using a clock signal. But that does not eliminate the forbidden node, because when clock is 1, if S is 1, R is 1, it will become 1, 1, still it will get the forbidden state. So how can we avoid that? Because it has advantage of ability to control it using a clock signal when S and R can go in, when it will be in whole mode. Clock 0 means whole mode. Clock 1 means transparent mode, so we can set and reset the value as we want. But the forbidden state 1, 1, when clock is 1, is still there. So how can we do that? Eh?
You'd add a NAND gate and then feed S and R into that, and then you would take that output and connect it into an AND gate with the output Q.
Okay. What you have just explained can be achieved even by a simple tweaking. So this is, but this is called clocked SR latch. This is called clocked SR latch. This is the basic SR latch. The circuit implementation of this clocked SR latch is this. As you can see, inside it, there is one inverter, another inverter connected back to back in the loop, and these 2 transistors, one of them is controlled by clock, and then the other 2 transistors provides the input connection S and R. This is the transistor level implementation of a clocked SR latch. This one still has the forbidden node, forbidden input problem, 1, 1. But as you can see, inside it what we have, it's a loop of 2 inverters. Every bistable latch and flip-flop is made of a loop of 2 inverters. But the problem we are facing in this one can be solved by a simple case. Put an inverter between S and R. So now, when clock is 0, these 2 input will produce 0 and 0. See, it will be in whole mode. If I set the value equal to 1 here, S will be 1, R will be 0. 1, 0, it will be 1, 0, it is in set mode. If I apply 0 here, From D, S is going directly, S will be 0. R is coming through an inverter, 1, 0 and 1, it will be reset mode, and under any circumstances, due to the presence of inverter, we will never have 1 and 1. So, by connecting the two lines of an SR latch together through an inverter, we avoid the possibility of having this forbidden state ever. So this latch will only have two allowed states, set and reset, when clock is high. So whatever you apply at the D will determine. If you apply D to 1, it will be set to 1. If you apply D to 0, it will be reset to 0, the output Q. That's all we care, right? And forbidden state will not be there. So an SR latch with an inverter, that gives the most popular latch in digital circuitry, D latch. So a D latch is made of an SR latch, an inverter and two clock signal. Here, so now, if your quiz question is implement the transistor level circuitry of a D latch, what do you do? This is the circuit. Draw here, it is D, put an inverter, right, to R, right? Sorry, here. From D, it will go directly, R, it will go through an inverter, right? So that is your transistor level CMOS circuit for a D latch. So D latch is very popular in digital circuit. So this is the D latch schematic diagram. So it avoids the forbidden state, but it can set, reset, as well as put it in hold mode, and the whole circuit is controlled by clock signal. So that's all. Now let's move to the next lecture. We have some time, but because these are related content, lecture 6, 7 and 8, these are very short lectures. I want to finish it as soon as possible because I want to have a lot of time on lecture 9 and 10. Okay. So, now in the last lecture we talked about dynamic sequential circuit. So, static sequential circuit, today we are going to talk about its dynamic version and some special type of sequential logic circuit. So now this is the static counterpart of a simple latch using the transmission gate as a switch. So the basic operation is here, basically it's a loop of two inverter. It's a loop of two inverter, right? We put a switch here and sometimes we put a switch here, right? In the loop. Sorry. Let's look at this one. So it's a feedback loop, one switch in the feedback loop, one switch in the input line. So the output node will get its value either from the input or it will maintain it through its own positive feedback, right? So output node in a static latch will not be floating. It will not maintain its value across the parasitic capacitance effective at that node. While it is copying, it is connected from D. While it is maintaining its value, it will have its own positive feedback. So it will always have a steady connection. That's why it is called static latch. On the other hand, if there is no feedback loop, just one inverter or two inverter in a chain connection, no loop. Let's look at one inverter version. Only one input switch. When the switch is on, a new value D will be copied at this intermediate node. And an inverter will produce its inverter. So where the Q will be available? Q is here. Q bar is here. when input is disconnected, when this input switch is off, the Q you have copied at the input of this inverter, the Q bar you have, but mostly this one is floating because this side is connected to the gate of the transistor in the inverter. It is insulated. This side is disconnected. So the node value Q is maintained by this parasitic capacitance effective in this node at the input of this inverter. So here, maintaining the value of Q depends on the ability of this capacitor to hold charge in floating state. Why it is floating? Because as soon as you are done copying input, this switch is off. So what type of logic it is, memory it is? It's a dynamic charge storage based memory. Anytime you have to maintain a logic value or memory value across a parasitic capacitance which goes into floating state, we call it a dynamic logic or dynamic memory. So while I am showing this single inverter version, theoretically we can implement a single bit latch using just one switch and one resistor. If we use this intermediate node as my memory node or storage node. But we are at the mercy of this parasitic capacitance effective at that node. So you have to carefully size the transistor in inverter to achieve the desired capacitance. But then again, we cannot hold like any dynamic circuit, we cannot hold that dynamic charge or information for a long time. Noise, leakage will distort it, so we have to periodically refresh it. So everything we have learned in lecture 5 about dynamic logic circuit applies to dynamic sequential circuit or dynamic memory circuit, because here we will be maintaining the memory value or information across this parasitic capacitance and it will be in floating state. So it will have all the pros and cons of dynamic logic circuit. Prospect is you can implement it with very bare minimum number of circuit elements compared to this one. So now, if I want to implement that master slave latch, this one, what? This one, the way it is designed, is it a positive latch or a negative latch? Who can tell? When clock is 0, this is on. And input will be copied to Q. So it's a negative latch, right? When clock is 0, you see clock bar is connected to NMOS, clock is connected to PMOS. When clock is 0, this PMOS is on. Clock is 0 means clock bar is on, this NMOS is on. So when clock is 0, D is copied to Q. That means it's a negative latch. If I switch the clock connection, I get a positive latch. So using dynamic sequential circuit or dynamic memory technique, if I want to implement the same edge triggered resistor or flip-flop we have discussed throughout previous lecture, the circuit will look like this. Is it a negative edge triggered flip-flop or a positive edge triggered flip-flop? No. The first one is negative, second one is positive. So negative followed by positive. This is dependent, this is controlling. So this is a positive edge triggered flip-flop or a single bit resistor. If I flip the clock connection, it becomes negative edge triggered, right? So that's why I'm showing it side by side. When you draw a latch or flip-flop or resistor, you can draw the static version and you can draw the dynamic version. So now let's look at the operation. When clock is 0, this one T1 is on, D will get copied here. When clock is 0, this one is off, so it will be maintaining its previous value at node B in a floating state. When clock is now 1, this one goes off, it will maintain its own value at node A across this capacitor in floating state. This one will be on, So whatever you copied here, it will travel through this and copy it at final Q. So in phase by phase. So now, again, this one will have clock overlapping problem. If in ideal case, if clock and clock overlap, clock and clock bar they are not overlapping, then we don't have to worry about relative delay of these two plus this. But practically in any circuit, clock and clock bar there will be an overlap. So the delay plus T1 plus I1, T1 plus I1 should be larger than this one or larger than the overlap. Otherwise, there will be a time when this one and this one both will be on. If the overlap time or on time is larger than the total delay of these two, it will contaminate the value which you are trying to hold. So careful sizing of the transistor need to be done so that overlap time related issue can be avoided. So ideally, clock and clock bar should not overlap, but practically there will be some overlap. So you have to carefully select the delay of these two, transmission gate and inverter, so that the total combined delay is larger than the clock overlap time. We can implement same circuit, much simpler. We don't need to use transmission gate. Very simple. Entire resistor can be implemented by two transistor and two inverter. First one, what is it? NMOS transistor controlled by clock. Second one, NMOS transistor controlled by clock bar. So this is a positive latch followed by a negative latch. This is a dynamic positive latch, this is a dynamic negative latch, right? No feedback loop. This intermediate node will be maintaining the value in floating state. Positive followed by negative, so it's a negative edge triggered dynamic flip-flop or single bit resistor. So the advantage is it is very simple, simplest possible resistor you can think of. Only two transistor, two inverter can give you a one full bit resistor, but it will have number one, all the problems of dynamic circuit. Number two, it will have a threshold voltage drop, making it even more vulnerable to noise, right? Floating node itself is a problem. Noise and leakage will distort the value here. But the value you are sending here through NMOS, if you are sending a 1, it is already distorted by a threshold voltage drop. So it will have all the disadvantages of dynamic circuit plus the disadvantage of threshold voltage drop to the NMOS transistor. So let's end here. Everybody is sleeping. So, yes, somebody wants to watch election results, so we will take the class Thursday. I already sent you the Zoom link. So my goal actually is to finish lecture 6, 7, 8 by the end of this week, so that we can have a quiz, one or two quiz on these 3 lectures. As I said, I want to spend a lot of time on lecture 10, particularly the memory, because if you want to do a microelectronics job, what are the companies other than Intel AMD? You can have a company in like Micron, the largest memory company in the world, or Infineon, second largest, or Samsung memory group, right? So either you go to logic design, CPU design, or memory design, and flash memory design and all those. So lecture 10 is the lecture to concentrate on if you want to go for a memory related so, once again, lecture 2, 3, and 10. In those 3 are the most important lecture, and then you can concentrate on 4, 5, and 6. Okay. So I will see you Thursday in class, and then Thursday again on Zoom.